So there's a couple things that are addressed by AP Chem and kind of the questions they get or give you that are a little bit different just in their wording or whatever than what is in the book, based on if you really understand the book or the lectures from the book, you would get this. But you know, obviously the goal is to make you do as well as possible in AP Chem. So let's look at some of those ideas from 1.8 that just AP Chem presents a little bit differently and help you to understand. So some of this information is kind of reiterating things I've already said. 1.8a1 and 1.8a2 are pretty straightforward. Basically, elements in the same group have similar properties in binding due to similar electron configurations. So, for example, an assessment of the standard could be something like this. Fluorine bonds with oxygen to form OF2. Based on this information, which below element also likely bonds in the form of OX2 and has similar properties? Okay, so we would look at our periodic table, right, which we're always going to be referencing all the time. And so we can see, okay, we have oxygen, this other compound is oxygen. What's going to be most similar to F and its properties? Well, something in the same group as F. What's in the same group as F? That's fluorine. So OCl2 is probably going to be the most similar in properties to OF2. That's it. It's understanding things in the same group have kind of similar properties. Okay, we could see something like that. This is the one that I think has a little bit more to it. It's basically applying this idea of ionization energies and seeing if you really understand it. This idea of 1.8.A3, typical charges of atoms in ionic compounds are governed by the number of valence electrons and predicted by their location on the periodic table. Okay. Now, again, we've already really talked about this, you've already read about it, but this is just another way to look at it to explain some of the problems you might see by AP Chem. So consider what we learned about bonding from this POGIL, and if you haven't gone over this POGIL yet, we will very soon. It's a part of Unit 1. And to simplify a little bit, you can see that here we have the oxidation of magnesium, and then here we have the reduction of oxygen. Now there's also the phase changes there, but nonetheless you can see, right, we can kind of simplify it to say that the crux of the energy here is the ox redox process, taking the elements from their natural state without a charge and reducing one, oxidizing the other. Now you can see that this requires energy. So simplifying the diagram a little bit, if the energy of oxidation and reduction are too high compared to the energy released when the ionic bond forms, the process will likely not be favorable. So look here. This, now we have MgO solid, so that is the ionic bond formation. And so remember, the removal of electrons is oxidation. That requires energy. Reduction can take some energy, can require some energy, or release a little bit of energy. But the driving force energetically of this process, which can make it favorable, is the release of energy by the formation of the ionic bond. So ionization energy is the energy required to remove an electron, and electron affinity is the energy change when an electron is added. Okay? So if we're talking about oxidation, that's ionization energy. And then electron affinity is reduction. Now, ionization energy is, again, the energy required to remove an electron. And ionization energy is always positive. It always requires energy to remove an electron. Remember, Coulomb's law, things are attracted to each other, right? So them coming together is going to release energy. It takes energy to pull attracted things away, like gravity. So if there's a ball on the ground, it's going to take energy to remove the ball and take it away from the ground. Electrons are attracted to the nucleus and therefore require energy to remove, always. And this is a misconception that you can hear a lot. Atoms want to lose electrons. If you're coming out of your general chemistry class thinking atoms want to lose electrons, no. First of all, atoms aren't alive, so we should never we can kind of in passing fun to introduce an idea, but we shouldn't explain what atoms really do in terms of anthropomorphization. I'm not sure if I'm saying that word correctly, but making atoms into people, okay? 2, removing electrons actually requires energy, the ionization energy, as electrons are attracted to the nucleus. Electrons are negatively charged, the nucleus is positively charged, they're attracted to each other. It will take energy to remove that electron. So, misconception. Do not say that atoms lose a certain number of electrons to get a full shell because that is stable. No. Okay? Even, let's say something like lithium, sodium, potassium. It requires energy to remove the electron. It requires energy to remove the electron. It does not make the atom stable. The atom does not, quote unquote, want to remove the electron. Now, sure, after oxidation, which requires energy, and the reduction of something else, which may require or release a little bit of energy, then there can be the ionic bond formation, which releases a lot of energy and can explain the favorability of the overall process. But it's not just that these atoms are, quote unquote, seeking to lose electrons. Remember, oxidation requires energy. So as per the image on the right, the energy required to oxidize and reduce atoms is inputted if the ionic bond formation releases enough energy to basically make up for it for the overall process to be favorable. Because we can see from where we started to where we finished, the ionic bond still results in a release of energy, even with the input needed for reduction and oxidation of the two respective elements. So how many electrons will an atom lose in these bonds? Well, as we will discuss in Unit 2 and covered in the lattice energy POGL, ions have a greater magnitude of charge. Ions with a greater magnitude of charge have a stronger lattice. Therefore, for example, it requires more energy to remove 2 electrons from Mg, making Mg2+, but Mg2+ will have a stronger lattice than a 1+ cation would. So for Mg, as compared to like sodium's just losing 1 electron. What am I saying here? This means that this amount, the oxidation of magnesium, is greater than it is of sodium, because magnesium is losing 2 electrons. But conversely, the amount of energy released here for magnesium is greater than sodium, because it has a magnitude of 2+, and therefore the amount of attraction to those anions in the ionic bond formation is going to be greater. So again, let's continue this question. What charge will certain cation make? Well, always ionization energy 3 will always be greater than ionization energy 2, which will always be greater than ionization energy 1, etc. In other words, each progressive ionization energy is always greater. This is because the number of protons stays the same within the nucleus, but electrons are being removed. Therefore, the cation has a positive charge, and the remaining electrons experience a greater attraction. An example of a greater effective nuclear charge. So as the atom is losing electrons, we're getting a cation with a greater and greater magnitude of charge, and therefore it requires more energy to remove another electron. There can be a large jump in ionization energies between electrons. This is usually because if enough electrons are removed so that the next electron will be removed from a lower energy level, then it will have a much stronger attraction to the nucleus and a larger ionization energy. Okay? So for example, if we have sodium and we have 1 electron in the outermost energy level, because sodium is 1s2, 2s2, 2p6, 3s1, we lose 3s1. Now the ionization energy for the second electron, i.e. 2, is going to be way higher, because the next electron is in a lower energy level and is closer to the nucleus, and so the attraction is stronger. And sodium already has Na+ already has a charge of +1. so that next electron is closer, so more attraction, and the atom has a positive charge, so more attraction, so that that electron will be way harder to remove, and in most situations energetically it will not be favorable to remove it because it's closer to the nucleus and more attracted. Okay? So it's not that it loses that electron and now has a full shell and it feels stable or happy or something. You need to explain that IE2 is going to be really high ionization energy because the next electron to be removed would be closer to the nucleus. And so the attraction goes way up. And so you can see something like this. What charge will sternification make? We see the electron configuration of lithium here. And then if lithium loses one electron after ionization energy 1, then we have Li+. Okay, so this would be ionization energy 1. Then we have Li+, so we'd have the ionization energy 2. And then for Li2+, then we have the ionization energy for that one, which would be ionization energy 3. What charge will lithium generally form? Looking at this, okay, be able to answer and explain the data and why. So go ahead and pause this video and think about it, and then when you unpause it, we can go over the answer. Okay, hopefully you pause the video. So the correct answer is it will form Li plus and end up with the configuration of 1s2. Now hopefully you understand looking at this too, right? Losing one electron. So Li going to Li plus, the electron configuration has changed, and that now there's one less electron. So that's why we're not writing 2s1 there, okay? And notice that there is a high jump in ionization energy from IE1 to IE2. Therefore, enough energy will not be released from an ionic bond formed in Li2+ to overcome the large ionization energy. So it would take a lot of energy to oxidize Li plus into Li2+. So this upward energy would be really, really big. And therefore, the amount of energy released in the ionic bond would probably not be enough to overcome it. And so the overall process is not favorable because it would result in a higher energy state than we're starting with. Therefore, lithium will just ionize to Li plus. And the other way we can explain this, right, we can see that the ionization energy is super high, right? And why is it? Well, notice the next electron's in a lower energy level. And so it's closer to the nucleus, it would take more energy to remove. Let's look at another one. Go ahead and look at the data here. What charge, whoops, have magnesium, we're looking at beryllium here. What charge will beryllium generally form in this one? So go ahead and pause the video if you haven't, and then we'll go over the answer. Okay, it would be the same for, this is supposed to be Be2+. Be2+. Notice that there's a high jump in ionization energy from IE2 to IE3. Right, see the big difference here. Therefore, enough energy will not be released from ionic bond formed in Be3+. It would be the same for magnesium, but to overcome the large ionization energy. Okay, so it's going to stop. It's going to stop after the second ionization energy. So we'll get 2 ionizations. So we'll end up with Be2+. But notice the third ionization energy is super high. And again, we can explain that looking at the electron configurations, because now if there's a Be2+, it's 1s2. So the next electron to be removed would be in a lower energy position, closer to the nucleus, so more attraction, so it would take more energy to remove. Okay, and that's what I was just saying. Be able to explain this. You should, if you're given a question like this, you should be able to explain this in terms of the electron considered in ionization energy 3, being in a lower energy level, closer to the nucleus, and therefore more attraction, so more energy to remove. Okay, so review of ionization energy in cations. With each progressive ionization energy increases as the cation becomes more positive, so there's more attraction on the electrons. Generally, concerning S and P block elements, when enough electrons are removed so that the next electron would be in a lower energy level, that energy level would not, or that electron would not be removed as it is closer to the nucleus and will have a very high ionization energy. If there is a high ionization energy, the electron will likely not be removed, as the overall process of oxidation and reduction followed by ionic bond formation will likely not be favorable, as there will not be a decrease in energy. This limits the amount of cations the amount of electrons of cations, I should say, the amount of electrons of cations lost and the resulting charge formed. Do not say that atoms want to lose a certain amount of electrons to be more stable. Losing electrons always requires energy. It is only favorable in the context of resulting bond formation. Okay, so that is ionization energy. Now, the other just part I want to talk about that is shorter but is related to this. Before we do, here's some example problems. So element X is the following ionization energies. Element X in chlorine would most likely form what? So go ahead and pause this video, look at the data, and determine what X will form with Cl here. Okay, so hopefully you paused the video and looked. And so you should get XCl2. Why? Because X will form X2+. How do we know that? Because the first two ionization energies are low, but then there's a huge jump. Okay, so that probably tells us this could be beryllium, magnesium, calcium, strontium in that group, because it can lose 2 electrons before the ionization energy goes way up for the third electron, probably because that next electron is in a lower energy level. Okay, let's look at another one. Element X is the following ionization energies. The element is, which of them could be the element? You might be like, oh my goodness, how can I know just based on that data? Well, look at the possibilities. If it didn't give you multiple choice, sure, that's not going to be easy. But with the multiple choice, you should be able to answer it. So go ahead, pause the video, look at the answers, and think about it, and then we'll go over it. Okay, so hopefully you pause the video. And the answer here is strontium. How do we know that the answer is strontium? Well, because we can see that there's a jump between ionization energy 2 and ionization energy 3. That's the biggest jump. What does that tell us? That tells us that this element is going to be 2+. And so the only one that's going to be 2+ that's in that group is Sr. Okay, so that is the answer. Sr2+ is indicated by this atom losing 2 electrons before a high increase in ionization energy. So generally, how many electrons can be removed? Well, group 1 to then become, for group 1, they're going to lose 1. For group 2, they will lose 2. But again, you should know and be able to explain the information that I'm giving right there, and based on like the ionization energy values that we were just going over, understanding that group 1, after it loses 1 electron, the next electron will be in a lower energy level, so the ionization energy will be way higher due to more attraction, Coulomb's law. And then group 2, after losing 2 electrons, the third electron will likely not be removed because its ionization energy 3, will be way higher because it will be in a lower energy level, and therefore closer to the nucleus, more attraction, Coulomb's law. Okay? D block cations are much harder to predict because it depends on varying D block configurations. So you can't really look at the same trends. So those questions I was looking at before are probably going to apply to like group 1 and group 2. I would think a lot of the time. Maybe if we're talking about like a 3+, it could be like a boron or aluminum, something like that. But not all the D block elements are going to follow the logic that we just carried out because it's a little bit more complicated. But if you have, keep in mind though, like if we have, for example, copper within a compound, well, if we have copper within a compound, we can determine what its charge is going to be. Like here, okay, CuCl, so we know that it must be Cu+. And generally within the context of a reaction, like if we have a double displacement reaction, Cu+ will stay as Cu+. It won't change to Cu2+. The exception to that is if we have an oxidation redox, like we'll have in Unit 9, where specifically the charge of the ion is changing. But in most cases, right, we can discern the charge of a D block element by, if it's not given to us, by looking at what's the oxidation number or the charge of it within the compound that would balance out the other charges. Okay. We also have, I'll just cover this, you might, a new topic. Well, this doesn't do justice to a separate video, because there's also electron affinity, and this is energy change when an electron is added, which is something we've also talked about. And so electron affinity 1 can be positive or negative. The nucleus is attracted to the added electron, but other electrons are repelled, okay? So because there's repulsion between the electrons when a new electron is added, but the electron is attracted to the nucleus, depending, this can either be a positive or negative value. So there's a misconception that the electron affinity releases more energy than the ionization energy requires. But that's not true. If you look at, like, for example, this example here, this reduction of oxygen actually requires energy, right? It doesn't release so much energy to make up for oxidation. No, reduction is not the driving process here. The driving process is, again, the formation of the ionic bond. And that's why I keep referring back to this image from this particular POGL for you to understand, right, that reduction can release some energy, but even when it releases some, it doesn't drive oxidation. It would be the formation of ionic bonds afterwards that is going to drive that process. So electron affinity 2 is always positive, and that's because the anion has a negative charge now. And so there's a negative charge to it, so there's repulsion between it and an additional electron which would be added. And so each progressive electron affinity value is more positive, meaning a higher energy than the previous. So they go up and up and up. So sometimes EA1 will be negative, but EA2 is always positive and always more positive than EA1. And EA3 is more positive than EA2, etc. And generally, a p block element will not add another electron when that electron would be on a higher energy level. And this makes sense. It's kind of the opposite reasoning of what we've already said. An anion has repulsion to additional electrons, and the electron would be further away. So it's going to be farther away from the nucleus, so it would have lower attraction. Okay? So it would take a lot of energy to add it, because the atom will have a negative charge, and that electron will be further away from the nucleus, so there's less attraction between it and the nucleus to make up for the repulsion happening between the electrons. And therefore, the electron affinity value would be very high, as in positive. Okay, so again, remember, electron affinities can be positive. And so you can see here, in this example again, going from O to O2 minus requires energy. Think about it. There's 2 electrons added. That first value for oxygen, I don't know off the top of my head if that's a positive or a negative electron affinity, but you can see that certainly EA2, electron affinity 2, is very positive, and so the process of adding those 2 electrons requires energy. And so we can use this logic to explain how many electrons or the resulting charge in an ionic bond that these p block elements will often have. So if we have like group 15, starting with nitrogen, generally 3 electrons can be added. A 4th electron would be added to the next energy level up, so it'd be farther away from the nucleus in a charged atom, and so it's generally not favorable, right? Because there's going to be a lot of repulsion, and that electron will have less attraction to make up for the repulsion, so it won't be favorable because it would require too much energy. And then we have the same logic, but in group 16, it would only take 2 electrons to reach that point, where the next one would be in a higher energy level with less attraction, so it wouldn't be favorable because it would require too much energy, and there's repulsion between the electrons. And then in group 17, when we just add 1 electron, then the next one wouldn't be favorable because it would be in a higher energy level. And so then we could also use the same reasoning for the noble gases, that the electron affinity values can be very high, because if another electron is added to give a noble gas a charge, that electron is going to be in a higher energy level, and there's going to be repulsion between it and the other electrons, but because the electron is in a higher energy level, is less attraction, so the electron affinity 1 is very high, which is why noble gases are often very unreactive, because it takes a lot of energy to ionize them, to make them a negative in this case, okay? And I'll just close with, when we look at the practice problems, the topic questions, etc., it seems to me that AP Chem likes, at least in Unit 1, to ask a lot more about ionization energy than electron affinity. I think it's because electron affinity 1 is a little bit hard to predict, whether it's positive and negative and such, and ionization energy is a little more straightforward. But you'll notice a lot of ionization energy practice problems based on the kind of logic we have